Hello, I'm Clay Morrison, and this is my Lab 5 lab report. So the purpose of this lab was to record the time it took for a magnet to fall through a tube of conductive aluminum foil, and then create a computer model of the same situation and compare the results to the observed data from the physical experiment. So the physical principles of this lab, first of all, were Faraday's law, which was used to find the current in each ring induced by the magnet, and then the Biot-Savart law, which was used to calculate the force exerted on each ring by the magnet. Then Newton's second law, which of course relates net force to acceleration, and that was used to model the falling magnet by writing position and velocity updating code in GlowScript. And then finally, Newton's third law, uh, which relates equal and opposite forces, and it was used to calculate the force exerted on the magnet by the whole tube, and then to calculate the net force by adding the gravitational force to this. So the procedures, first of all, for the physical experiment, a bar magnet was dropped through an aluminum tube 5 times, and the process was recorded using a smartphone, and then the times were retrieved using a scrubbing tool on a video editing app, and then the same situation was modeled using a GlowScript code that included the physical parameters used in the first part, and then the magnetic dipole moment from Lab 3 as well. So the experimental results are shown here. This is my result. These are my results for each trial. Then I plugged into it to Excel and got the average time, which I got to be 1.214 seconds. So getting into my code here, it was pretty long, so I'm just going to go over the parts that I edited. So for the first part, I have my length of the tube here, the width of the foil, the inner radius of the like the cardboard part of the tube, and then the total radius achieved by adding those. And then here's my magnetic dipole moment calculated from Lab 3, and then that was used to, and as well as the mass for the bar magnet, and these were used to visualize the bar magnet, as you can see down here. And then so this is a function that calculates the magnetic field on the bar magnet, and it was just copy and pasted from Lab 3. And then down here is a function I wrote to calculate the magnetic flux. And then getting over here, this is the gravitational force on the bar magnet, F grav. And then down here, basically just calculated the magnetic force from the tube onto the magnet. And then this calculates the current in the ring. And then getting down here, you calculate the magnetic field at each ring, and then the magnetic force on the magnet. And finally, the F net, you just basically just add the gravitational force and magnetic force. And then this down here just updates the velocity and position of the magnet. So my model is shown here. This was after it was run, so it started from the top and ended up at the bottom right here. And this is my graph. It looks pretty good. Theoretically, it should level off down here, which it does. And then the time was 0.472 seconds, which was lower than expected, but I'll get to that in a bit. So I'm interpreting the simulation. So which is basically asking which color represents corresponds to counterclockwise or clockwise, and as you can see, this was blue right here, and I would say that's counterclockwise because the magnetic or the flux of the magnet is pointing downwards, so it induces the counterclockwise current around the tube. And then what would happen to the dynamics of the system if you flip the magnet? Well, it would. So the current would turn clockwise because the flux is going upwards, and then clockwise is red, of course. And like I said back here, the comparing the times, this is a lot lower than the physical time I got, which I theoretically should be because I had a high magnetic dipole moment at 5.53, so I think that relates to it. And what does the shape of the graph tell you about the forces acting on the bar magnet? Well, since the graph levels off down here and the velocity increases, it shows that the forces increase as the magnet falls, and it reaches somewhat of like a terminal velocity right here. So getting into the what if questions, if the resistivity of the conductor were reduced to as close as possible to zero, that would change the dynamics of the falling bar magnet because it would slow it down because the current becomes larger according to Ohm's law. And if holes were cut into the tubes, this would affect the ring current in the models because it lowers the amount of complete rings and creates a smaller overall magnetic field. So that ends my presentation. Thank you for watching.